Man, I love it when things actually work. You can't hear it, but this system is up and running. I recently expanded my array so I could cover 100% of my power consumption. I made a video on the expansion if you want to see the details. I kept all my standard panels and just repositioned them to the bottom row and then added a new row of bifacial panels across the top. My 7.6 kilowatt grid tie solar edge inverter couldn't make use of all those extra panels, so it's an opportunity to try out some new inverters. Today, I'm going to give an overview of the connections, the setup, and the performance of the new EG4 12KPV all-in-one inverter, and the EG4 Wallmount battery. Welcome back to Projects with Everyday Dave. Let's check out the real-world performance of the very popular EG4 12KPV. The first inverter I tried for this expansion was a very inexpensive SunGold power inverter, and it ran for over a year with no problems. The hardware was working fine, but finally the software was really difficult to use, and the fans were exceptionally noisy. Then just a couple months ago, I had a software issue that caused the unit to stop producing power. I was able to get it to work again by updating the firmware, but then the fans were running all the time. They wouldn't even shut off at night, and I just didn't want to take the time to figure out what the problem was. So I finally decided to purchase this 12K PV unit from Signature Solar and see if that would get the job done. So far, it's been great. It was super fast to set up. It took me about 2 hours to mount it, place the battery, make all the connections, and have it producing power. Mounting it was relatively simple. All I had to do is screw a cleat to the wall and hang it up. Fortunately, my son was here over the weekend and was able to help me put it in because it definitely requires a team lift to install.
Whew, that's heavy. That's way heavier than that one.
Adjusting the settings to get the operational mode I was looking for required a call to Signature Solar. There are a lot of options in this unit, and it's not quite as straightforward as you would think just by looking at the settings. After a few minutes on hold, I was able to talk to a live person who walked me through all of the settings I needed, and in just a few minutes, I had it doing exactly what I wanted it to do. I can't tell you how nice it is to be able to just call somebody up and have them help you solve your problem. This was actually the easiest setup I've ever done for installing an inverter. The only thing that's easier is microinverters, and you pretty much just plug them in and they work, but they only do one thing, so that's not really comparable. You might be wondering why I chose the 12K instead of the 18K, and the short of it is, it's the cheapest solution that will meet my current needs. Also, if I can run all the big equipment in my house, like my heat pump, my well, all my big power tools, then you and I can both be sure that the 18K will be able to do it as well. If I started with the 18K, then how would we know if the 12K would work? Since this is a transformerless inverter, I was most curious about the big induction loads. Battery's charged up, let me switch off the grid and we'll see if it works. The first thing I'm going to check is my 4-ton heat pump. Now, I do have a soft starter installed, and without that soft starter installed, I'm pretty sure it would not work. So small AC units, probably no problem, but very large units like this, you're going to need a soft starter. All right, the unit is disconnected from the grid. Now I'm going to turn on the AC, and we'll see what it does. Put the microphone next to it so you can hear it start up. The pump coming on. Relay clipped. Soft start's running. There we go, started right up. There we go, it started right up. And that sounded really similar to starting up on grid power, so I'm pretty happy with that result. Seemed to have virtually no trouble at all. And there the app finally caught up. The one thing I don't like about this app is it's about a minute behind. So it's really hard to do things like this and show the instantaneous activity, but it's caught up now, showing about 2,000 watts, so really this doesn't pull much more than the air compressor. Well, that worked great, so let's try some power tools. Okay, I ran an extension cord to the off-grid sub panel that's powered by the 12K. Now we're going to run some power tools. I'll start with the table saw. That's a pretty difficult one to power up. Once it's powered up, it shouldn't have any problem cutting, but we'll do both. Nice, no sweat. Let's try some others. All right, this one's always the biggest challenge. Let's give it a shot. All right, I'm pretty happy with that. This is one of the hardest tools to fire up. It has a lot of inertia to get rolling with those big blades. And most of the transformerless inverters I've tested can't run this thing. So that's pretty good. All right, I've plugged in the compressor. This one's also pretty tough to fire up. Now that we have some of the important things out of the way, let's look at some of the other specs. I made a chart comparing some of the more important specs between the 12K and the 18K inverters. For starters, the 12K is $1,400 cheaper than the 18K, and if you use my special code and the link in the description below, you can get it even cheaper than the current discounted price. On the outside, they don't look that different from each other. The 12K is just a little bit shorter and 11 pounds lighter than the 18K. They're both split-phase transformerless inverters, so you can get 120, 240 out of a single unit. The 12K has an AC output of 33.3 amps or 8,000 watts, and the 18K can produce 50 amps or 12,000 watts. Now keep in mind, you're only getting half of that per phase. Think of the 12K as having two 4,000 watt inverters packaged in one unit. Each phase can support 4,000 watts. On the 18K, each phase can support 6,000 watts. For surge capacity, for some reason, the specs for the 12K and the 18K are recorded a little bit differently. The 12K can handle a half a second spike of 16 kilowatts, and it can do a sustained 8.8 kilowatt load for 12 minutes, which is a pretty nice margin. The 18K apparently has some extra headroom when the sun is shining. With PV, it can sustain 15.5 kilowatts for 5 minutes, and without PV, it can sustain 13.5 kilowatts for 10 minutes. Now let's take a look at the solar. There are some significant differences in the solar specs that might drive your decision between the 12K and the 18K. The 12K has two MPPT trackers. Each of them are capable of 25 amps, but the total is limited to 41.6 amps. Both trackers have two inputs, so you can connect parallel strings at the inverter without adding a separate combiner box. This will allow you to have up to two different spec solar panels or solar panels facing in two different directions. The 18K, on the other hand, has three trackers. This is really helpful. With three trackers, you can have three independent arrays. For instance, you could have one facing east, one facing south, and one facing west. And that would allow you to optimize the system performance while limiting the amount of clipping that you see during the day. However, you have to keep in mind the 18K has only one tracker with dual inputs and the higher 25 amp rating. Personally, I don't think that's a big deal. I am rarely looking to put two strings in parallel on a single input. For voltage and operating range, they are almost the same. Both have a DC input range of 100 to 600 volts DC. As far as I know, that's the best anyone offers. The advantage here is you can put many more panels in series, reducing the amount of copper that you have to run. When sizing your strings, make sure that the voltage open circuit for the string is below 600 volts, with some margin. Now, even though your string is allowed to be up to 600 volts, you need to pay attention to the voltage operating range. And what you want to do is make sure that the voltage maximum power is under 500 volts. That way, when the system is under load, it'll be under the 500 volts where the tracker is actually operating. Even though the minimum voltage for the 12K is 120 and 140 for the 18K, I would target a minimum string voltage of 300 volts. The higher voltage you have, the more efficient you're going to be operating. The maximum usable PV for the 12K is 12,000 watts, but the inverter is only capable of making use of 8,000 watts, so you would only be able to take advantage of the additional 4,000 watts if your batteries needed to be charged. I'll just use my setup as an example. Right now, I have two strings connected. I have 9 375 watt Mission solar panels at the bottom of my array. The voltage open circuit is 48.2 volts times 9 panels. That's 433.8 volts. So there's no concern there. We're well under the 600 volt max. The voltage maximum power is 39.8 volts times 9 panels. That's 358.2 volts. That puts us right in the sweet range for operation. In fact, I just checked mine a little bit ago, and it's a totally cloudy day, but that doesn't affect voltage that much. And we're actually operating at 360 volts, right around there. So the voltage maximum power is a really good metric to use for setting that target voltage. It's really temperature that drives the voltage. So if you live in a place that's really cold, pay attention to your voltages because they'll probably be a little higher than what the specification says. My other input is connected to 11 390 watt Canadian Solar bifacial panels that are along the top row of my array. The voltage open circuit for those panels is 46.8 volts times 11 panels, that's 514.8 volts, so no concern there for exceeding the maximum. The voltage maximum power is 38.3 volts, times 11 panels would put us at 418 volts. That's between the 120 and 500, so we should have no issues there. And that string is currently operating at about 418 volts. If I take the 3,375 watts from the lower string and the 4,290 watts from the upper string, then I have a total available input of 7,665 watts. Now, more than half of those are bifacial panels, so with the right conditions, I could see even more than the rated output. In fact, this would be a good time to show the operational characteristics with my current settings. I currently have the system set up for PV priority and export any extra power. At night, I have it set to use up to 70% of the battery to support loads before supplying power from the grid. It's a partly cloudy day, so the PV is fluctuating a lot. This first scenario shows the battery is full and there is no load, so 100% of the over 6,000 watts that's being generated is being exported to the grid. Now, when I turn on my heat pump, you can see almost 2,000 watts supplying the loads, and the remainder is exported to the grid. It's pretty cool to just see it seamlessly direct the power wherever it's needed. Now, it can add a little bit of imbalance to the system by plugging in my single-phase 1,500 watt, 110 volt water heater, and that boosts the consumption by over 1,500 watts and pulls the export down to about 700 watts. If I drop the 110 volt water heater and instead replace it with a 240 volt 5,000 watt water heater, you can see it start to use the grid to balance things out for a second, and then it settles out, supplying most of the load with PV and the remainder with the battery. After running the loads above the nominal 8,000 watt max for a while, you can see a few hundred watts are starting to be supplied from the grid to keep it within spec. You can see a big jump in the power. The sun must have come out from behind the clouds for a second because we're exceeding the rated output of the array. Remember, the panels only total 7,665 watts, but now we're seeing over 8,000 watts come in. If I speed up the activity, you can see the system constantly balancing, only bringing in power from the grid periodically when the consumption is too high for too long. Now, if I push it even harder by combining the 240 volt 2,000 watt heat pump, the 240 volt 5,000 watt water heater, and the 1,500 watt 110 volt water heater, you can see the grid pick up to 1,600 watts to keep the inverter right around its 8,000 watts max. Finally, as I drop the loads back down to just the heat pump, the PV supplies all the needed power. The battery is almost full, so the remaining power is all exported. Then I was thinking, what if the inverter won't be able to start the heat pump if it's already under a big load? And what if it's robbing a little power from the grid and just not showing it? So I decided to make things as challenging as possible. I shut off the breaker so there is no possibility of grid feeding in. I also added a 5,000 watt load from the hot water heater. And to make it even more challenging, I made sure the battery was at a low state of charge. You can see that the battery is only at 50.4 volts, and the PV is almost non-existent at under 200 watts. I lowered the temperature on the thermostat and waited to see if it would come on. And finally, unbelievably, it kicked on and started right up just like before. I couldn't even tell a difference. Because the battery was already so low, it didn't take very long to pull the voltage under 50 volts. With the system maxed out at nearly 8,000 watts and no support from PV or the grid, the fans are running pretty much full tilt. If I put the mic next to them, you can really hear them. When I turn off the load of the heat pump, the voltage pops back up a little bit to just over 50 volts. I am truly impressed. The battery was at a low voltage, the inverter was preloaded to 5,800 watts, and I was able to start my 4-ton heat pump. That is pretty amazing. Man, that is so much fun. It brings me so much joy to see everything so perfectly managed. All the power coming in from the sun, pushed out to the grid if needed, filling the batteries if needed, supplying the loads, balancing every one of those components around. I just love how these systems have matured over the years. It is so fantastic. There are a plethora of ways to configure the system, and I can't demonstrate them all, but hopefully this gives you a pretty good idea of how the system can work and all the different things it can do and how smoothly it can do them. All right, back to our chart. That was a bit of a rabbit trail. I could add a few more panels and still be within the voltage range, and that would certainly help on cloudy days. But you can see the current configuration is a pretty good fit on sunny days. No real need for me to push it up to 12,000 watts, because my SolarEdge inverter can balance the rest of the panels for the time being. Finally, at the bottom of the chart, the warranty is 10 years, and that's pretty respectable in the industry for these all-in-one inverters. Now, my SolarEdge inverter is 12 years, and you can purchase an upgrade up to 25 years for that inverter. But these days, technology is changing so fast, I can't imagine I'll be using this inverter 25 years from now. But who knows? I love the new form factor of these wall mount batteries. They're made possible by the new higher capacity prism cells. These cells are 280 amp hour. I recently built a version of this style of battery with 304 amp hour cells. It was a lot cheaper than this battery, but it's missing some key features. There are several advantages to this form factor that I really like. First of all, they take up a lot less space in the room. My server rack battery takes up a lot more usable floor space. Since every cell is directly balanced with the BMS, you have less of an issue with one battery drifting off with a different state of charge. This pack is connected from corner to corner instead of through a bus bar, so it's a little bit more problematic. But either way, if you don't charge it to 100% state of charge every few days, the state of charge of each one of these batteries starts to drift from nominal. The third big improvement is a reduction in cost. I made a chart here to compare the wall mount battery with a similar server rack setup. To make as close of an apples-to-apples comparison as possible, I'm comparing one wall mount battery, which is 14.3 kilowatt hours, to a 15.3 kilowatt hour package of 3 EG4 LLS server rack batteries in a 3-slot rack. So imagine just a rack of 3 server rack batteries instead of the 5 that I have shown here. The wall mount version is $231 per kilowatt hour, and the server rack setup is $278 per kilowatt hour. If I nominalize the cost of the server rack battery to the same capacity, it would be $3,977 or $678 more expensive than the wall mount version. So clearly this is a much more cost-effective package. The wall mount battery is a little bit taller, but the dimension that really matters is the distance into the room. And the server rack batteries come way further into the room, reducing the amount of usable space, in my case, in the garage, and that's a big factor. The cycle life is slightly better for the wall mount battery. I'm not sure exactly why that is. They might be a different source for the cells, but either way, it's still a leg up for the wall mount version. You get slightly more capacity with the 3 server rack version that I'm comparing here, but I imagine that they'll come out with a 300 amp hour version of this wall mount battery at some point. Like I said, I did a DIY version, and the one I built was 304 amp hours, and it would be the same capacity as this 3 server rack battery package that I'm comparing to now. The server rack version does have a max current advantage. Each server rack battery has a 100 amp BMS, so combined that gives you 300 amp max as opposed to the 200 amp max BMS on the single wall mount. If you were installing an 18K instead of this 12K, for instance, you would want 2 wall mount batteries to give you the necessary current levels to support that inverter. Combined, that would give you a 400 amp max output. The wall mount has a couple additional features with dual onboard fire arresters and a self-heating feature. They both communicate with a wide range of inverters and come with a 10-year warranty. In some situations, the server rack battery still might make more sense for you. You might want just 1 or 2 batteries for your setup, and in that case, they're a lot lighter, easier to manage, and it'll be more cost effective. But I think for most people, you need at least the capacity of one of these wall mount batteries. So this is really probably the easiest choice and the most cost effective choice for any kind of home backup. I have this temporarily wired, but it's close enough to give you a quick overview. I didn't install the wire chase connecting box to make it easier to illustrate, but if you're doing a permanent install, I would recommend getting the wire chase. It covers everything up, keeps it really nice and neat and clean, and makes sure that no one accidentally contacts something that they shouldn't. Before you do your wiring connections, make sure everything is off. Make sure that the battery switch is off and the battery breaker is off. Make sure that your PV is disconnected at the source and the PV switch on the inverter is turned off. Make sure the breaker for your incoming AC connection is off, and make sure your load generator and battery breakers are all off in the inverter. Then make sure you take off any jewelry like wedding rings and things like that, and it doesn't hurt to wear some rubber gloves just for a little added protection. Starting with the battery connections, it's very simple. Connect the orange cable to the CAN port and select the dip switch to 1 for one battery. If you have multiple batteries, you'll need to look in the manual and set the dip switches accordingly. This has a really nice set of bus bars so you can connect multiple batteries together, and if you have an 18K, you'll be running 2 cables in parallel, so you'll have sufficient capacity for the 400 amp load. Since we have one battery and it's only 200 amps, then we can just use one set of 2-watt cables. You'll have a ground connection. You need to connect this to the ground system to your house. I connected it to the ground bus bar, and that's it for the battery. Now, if you have 2 batteries, you'll connect them to these additional bus bar connections. There's 4 ports, so really convenient for extra connections. By the way, if you're finding this content helpful, consider hitting the super thanks button down below. It would really help out the channel. Also, you can leave a donation at my website, projectswithdave.com. I have lots of helpful resources there for you, including exclusive discounts to help you get your solar system at a lower price. The wiring for the 12K itself is really simple. The first thing to connect is the battery cables. There's 2 2-aught cables that need connected. At the battery end, they're very simple to connect. There's a button on the side that allows you to easily remove them. You simply press them in, they snap, super easy. These are 2-aught cables, just plenty for the 12K. If you have the 18K, you'll be running 2 sets of these. There's 2 sets of terminals. Make sure you achieve the rated torque for each one of the mounts. They're all in the manual. When you make your connections, make sure you put a little bit of a service loop in them so you're not putting too much load on the terminal. You can see all of my AC and DC wires have a little bit of a loop on them, and that's just a good practice, especially if later on you make a change, you can reach the new location. Or if you need to cut the end for some reason and extend it, you have a little bit of wire to work with. It's just a good practice. Once you have the DC cables connected, you can connect the grid input. You have a line 1 and a line 2. You'll want to use 6-gauge THHN, and you'll want to put that in a conduit. This one here is just Romex because it's temporary at the moment, but you'd want to use a conduit for each one of those. For the grid inputs, there's included CT sensors. You put one on line 1 and one on line 2. Then you'll run the neutral to the neutral bus. For your load, you'll run 6-gauge THHN, line 1 and line 2 to the 2 inputs to the breaker, and then neutral to the neutral bus and ground to the ground bus. Be sure and connect your ground bus to your household ground system. Probably wouldn't hurt to use a 6-gauge ground wire for that. On the PV side, you'll want to run a metal conduit to your inverter or your wire chase. In this case, we have 2 sets of inputs. 2 inputs for tracker 1 and 2 inputs for tracker 2. In my case, I have my row of bifacial panels going into one tracker and my row of standard panels going into the other tracker. If I really wanted to max out this system, I could take the entire top row of bifacials and divide it in 2, put half of them into one and half of them into the other. Now, I would end up with a lot of clipping because I can't really make use of a whole lot more than I'm currently putting in. For most cases, if you just want 8,000 to 12,000 watts, you can probably do that with just 2 strings. If you really want to max out the input, then you can put parallel strings into each one of these sets. Just make sure that the strings that you're putting in parallel exactly match. For the communications, there's simply the battery communication goes to the battery connection point, the far top left terminal, and the CT sensors go into the plug right next to that. Once all the connections are made, you'll be able to power the system up. You turn the battery on and connect power to the battery, confirm your firmware status, make any updates you need to make. Once you have all your settings set, then you can turn on your grid, load, and PV. So overall, the connections are really simple. There's not that many to make. I was able to hang this on the wall, make all the wiring connections, and do the settings within 2 hours, have it up and running. Now, I already had the main wires running to the system, but otherwise, it's not that difficult. All right, I'm going to go over some settings with you here. I'll go over the ones I currently have mine set for, but as I go through it, I'll explain some of them, and hopefully that will help you choose your settings or understand what kind of settings can be selected for this inverter. So here we're on the main page on our monitor, and to change the settings, you'll click here on Maintenance. And then at first it looks blank. You'll need to hit the Read button, and that brings up all of the settings as it reads them from the inverter. I'm not going to go through every setting, but just some of the key ones that we need to have for the inverter to operate the way I have it currently operating. So first of all, you'll set your time. You'll set your PV input. In my case, I have two inputs, PV1 and PV2. Set your startup voltage. For the 12K, that can be as low as 120, and for the 18K, it can be as low as 140. I have mine set at 140. So if you want to make a change, you can just type it in, like let's change this voltage from 140 to 150. And then hit set. And you'll get a message saying that's successfully set, so that's the new start voltage. For measurement, we'll be using the CT sensors, and I have installed them in the right direction, so I don't need to reverse the direction, but if you put them in backwards, you could reverse it. For battery type, I'm using a lithium battery. Now, I did have a problem where the state of charge of my battery wasn't matching the actual, and I called up Signature Solar. They had me change this to lead acid and make the settings by voltage for a week and do a complete full depth of discharge. Then I was able to turn it back to lithium settings, and now the state of charge registers correctly. So if you have that problem, you can just call them. They'll go through those settings with you, but it wasn't terribly difficult. For most of you, you'll have lithium settings. If your battery does not communicate, you're not using an EG4 or one of the other compatible batteries, then you might have to set it on lead acid and control the battery by voltage. In this case, we have an EG4 battery. Then brand. You might think selecting EG4 is what you would do, but in this case, any EG4 battery that does not have a screen is 0, and any EG4 battery that does have a screen is 1. In my case, it's an indoor battery with a screen, so we'll select 1. This tells us our firmware version. Now I can move on to application settings. In my case, I have a battery and I want to use it for backup, so that's enabled. And I have it connected to the grid. I want to be able to sell back, so that's enabled. I do have arc detection enabled, so if there's a problem with the array, this will help detect it. Over here on grid sellback, I want to be able to do the full 8 kilowatts, so I have that set to 8, and the rest we'll leave on default. Since we'll be operating by state of charge limit, I have that set to 100. I do not have a parallel inverter, so these are the settings that I need for that. I have a 60 Hertz frequency grid, and that's standard, and it's 120/240 split phase. Now for the charge settings menu, we will be controlling by state of charge instead of by voltage. Our charge current limit is 160 amps. Now for AC charge, I have that disabled because I am going to be going with PV priority charging. So that's this setting down here, and I have that as enabled. What that does is, if solar is available, it will supply it to the loads, and any extra will go to charging the battery. If the battery is full, then it will start exporting to the grid. So since this is disabled, I'm not going to worry about the rest of these settings. For PV enabled, I will be concerned about these settings. I want it to charge to 100% when PV is available. I want to be able to use the full 8 kilowatts for charging the batteries. And then the voltage isn't a huge concern here because we're going with state of charge. I don't have a generator connected, so I don't need to worry about these settings. I just have it disabled. For discharge settings, we're going by state of charge. Now the way this will work is, as long as I'm on the grid and there's no PV, it will pull from the battery until the battery drops to 30%. Then it will switch to grid power. If the grid is disconnected, it will drop as low as 20%. If I wanted to have more reserve in case the power went out in the middle of the night, I could change this to like 50%, or I could change the grid cutoff to less than 20%, but the recommendation is to never go less than 20%. That will maintain the life of your batteries the best. So here I have 10% of battery to work with if the power goes out in the middle of the night. Forced discharge, I have that disabled. In the forced discharge, this is disabled currently, but if you had a time of use you were trying to achieve, you can put in the amount of discharge you want to go down to, and then the start and end time where you want to push that power out, and then this would be the setting for which you would put how much power you want to put out. And I've messed with this a little bit. I've had settings where I would discharge during the day, and I would have it set to 3,000 watts. If there was only 2,000 watts of PV, then I would be putting 5,000 watts out to the grid. And if there was no PV, I'd be putting out 3,000 watts to the grid. But for the most part, I just have that disabled. And then we have peak shaving settings here. I'm not doing that. I have the same power rate no matter what time of day I use the power. So there's really no reason for me to mess with this. But if you have different prices during the day, you might even use the battery to be charging the battery at night. You could have the battery charge overnight and then discharge the battery and put solar to the grid during the day, as long as it was less than 8 kilowatts. I don't have any AC coupling, so that's disabled, and smart load is also disabled. So I think that's all the settings that are super important to understand. Now that you have a basic idea of how it operates, you can probably figure out how to make changes for achieving what you're trying to achieve. Now, let's quickly look at some of the data that's available. So if I click on monitor, this is the main monitoring page. It shows you the status of everything, how much PV is being produced, how much is going to the battery or from the battery, to the loads, or I guess it doesn't come from the loads, but to the loads and to or from the grid. And then from a data standpoint, there are a lot of things you can look at, and this is really fantastic. I can look at the watts being produced on each string independently, and this shows the profile during the day. I can look at the state of charge of the battery. I can look at the voltage of the battery, the charge and discharge power. You can see I was discharging the battery to the grid. I had it set for about 3,000 watts. And then when the sun came out, it would regulate that depending on how much solar was available and the output capacity of the inverter. On the power to grid, you can see it's bouncing around a little bit as it switches between the battery and the PV input, trying to manage those. And I don't know if it actually drops to 0 when it's doing that, or if that's just an anomaly in the data, because when I look at it, it's pretty much just holding 8,000 watts. But lots of great data here to help you see exactly what's going on with every part of the inverter. I really like this setup. And then there's other charts you can compare things like the PV output for PV1 and PV2 for the day, for instance. And I can compare the bifacial string, which is putting out more than the standard string. You can look at the energy produced on each given day. I can download all of that available data for every piece of information that's there and export that to Excel and analyze it. So overall, I'm pretty happy with the interface. There's a lot of standard things available and a lot of data that you can manipulate and download and evaluate on your own. So far, no complaints with the interface and what I have available to use. Wow, that was a lot to cover. If you want to purchase a 12K or 18K inverter or one of these wall mount batteries, be sure to save some money by using the discount code from the description below or by going to my website, projectswithdave.com. If you want to see a step-by-step install of a smaller off-grid Victron system, watch this video right here. If you want to see my step-by-step expansion of my entire solar array, watch this video right here. I plan to do a lot more testing with this inverter, with different solar configurations, different batteries, so be sure and subscribe so you don't miss out on that content when I finally put it out. Thanks for watching, and I'll see you next time.